Well, thanks. First of all, thanks for having me up to the club. Yeah, great. I mean, I think it was Darren Salter that said that you guys have presentations from time to time. So he knew I sort of built various pieces of stuff, and said, "Oh, why don't you why don't you come up and give a chat on your tune, your Magloop tuner?" So I mean, I don't know if anybody's used magnetic loops before. Oh, right, okay, we've got one person then. So my name's Dave, G7IYK. So I was licensed back in like 1991-ish, and my background is I'm electronics engineer. Always have been, and it's more specifically a chip designer. So I do sort of chip design for like Wi-Fi, Bluetooth, that sort of stuff, and I've done a bit of 4G and LTE as well. So so I split this sort of talk into what I would consider to be like 3 sections. I'm going to talk a bit about the actual loops, because you kind of have to have a concept of what they are in order to realise why we need to design a tuner in the first place. So we'll have a little bit about the loops, and then I was going to do a demonstration of the tuner, said tuner, and so it's currently hooked up to the big loop. The small loop I only built last Sunday, so it's not got a motor on it at the moment, whereas the big loop's motorised. So I'll do a demo of the loops, and then after that I was going to do a little bit more detail on how the tuner actually works, from a design point of view. The only bit I'm probably not going to go into too much detail on is all the software on the tuner, because that would be a whole talk in its own right, and everybody will probably be bored out of their minds. So I won't bother with too much about the software. Just stick to how the hardware works, really. So yeah, any chance can we have those front lights off? Maybe does that work? Because some of the diagrams are quite detailed, and I've got a feeling they're going to get lost in the brightness of it all. And hopefully, that's much better. Yeah, that's better. There we go. You can see it now. Okay, so so we'll have a little talk about the loops. Hopefully this will. Hopefully. Oh. Why is that not working? Hang on a minute. So it starts with me to go on. Where did that go then? Pushing the left-handed, pushing the up button rather than the down button. That'll be it. Okay, so yeah, magnetic loop antennas. So essentially, that's the structure of a magnetic loop, and it's pretty easy to correlate that diagram with these actual loops. So you've got a large conducting element with a capacitor at the top. So they're obviously these are airspace capacitors at the top of the loop. And then at the bottom you've got some people call them a Faraday loop or a coupling loop. So the large loop is not in any way physically connected to any drive. It's completely passive, and the power is driven into the lower loop. And effectively, what it is a tank circuit or a tuned transformer, if you like. You excite the large loop with RF power into the lower loop, and then it resonates, just like any other antenna system does. And the reason you need the capacitor at the top, as will become apparent, is to actually tune the whole affair. And then the loop, the frequency you want the loop to sit at depends on the diameter of the loop or the circumference of the loop and the capacity you use. So for example, the little loop is optimized for 10 meters. That will do 10 meters, 15 meters, just goes down across the bottom of the 20-meter band down to about 13.9 meg. And then the big loop is optimized for about 40 meters. So that does 40 and 20. Well, you could get the little loop to go down to 40, but it'd be so horrifically inefficient, there wouldn't be much point using it. So, you've got to kind of scale the loops for the band spread you want. So let's just go through some of the key points then. So it's obviously a small footprint antenna. It's great if you haven't got any room, like a lot of people use them on balconies or in a little garden where you can't put up a beam or a huge, great long wire. It's highly efficient, very narrow bandwidth, and a very low radiation resistance. By that I mean the actual loop itself is very low, very low resistance. You can see that this is made, the loops, I make them out of heliacs, which have got an outer copper skin, and they're extremely low resistance, which, well, as I'll come on to, is quite important. They're very low noise compared with a traditional antenna because it's very narrow band. Extremely narrow. So also almost acts like a pre-selector on the front of your radio. So, I mean, for example, I was trying that 10-meter loop out on the weekend. Compared with a 130-foot long wire, I was getting about 2 S points less noise from the loop compared with the long wire, and approximately the same level of actual signal from people I was listening to. So it's quite low noise. It's great if you're in a noisy environment. They're directional in the plane of the loop, so they're directional. The lobes come out this side and the other side. They're directional in that plane.
Did you mean aimed on?
Say again, sorry?
Did you mean it's aimed on?
No, they're both symmetrical, sort of out both sides of the loop. Is that what you mean?
That one's pointing at me.
Yeah.
Radiating in my direction, or is it radiating that way?
It's radiating in this direction. So in that plane, so the lobe is coming out this side. The null goes through the middle. Yeah, when we say null, it's not a big null, but it's more directional in that plane. Obviously, you can use them across multiple bands. They don't require a ground plane of any description. You don't need a ground plane because of the way they work. I'll get into that. They don't require high elevation. They usually work. Optimum height is about a loop diameter, maybe a loop and a half. That's as high as you need to put them. If you put them any higher, they actually don't work as well. So, which is sort of counterintuitive compared with like a traditional, dipole or long wire or whatever. This is an interesting point. They're vertically polarized at low angles and horizontally polarized at high angles. So you get all the advantage of ground wave at low elevation and sky wave at high elevation, which you don't get with a traditional antenna. A vertical will tend to be polarized more towards the sky wave, whereas a long wire is more polarized at low elevations. I think that's the right way around. So if you compare the efficiency of a short or a full-size vertical with a small loop antenna, what you're trading off ground dependency, i.e. the use of ground planes, and earth losses. You're trading that off against a much easier and controllable conductor losses in the loop, and also the ohmic losses associated with the capacitance and the interconnects. With a Magloop, what you absolutely have to make the optimum way of doing it is to make sure the connection between the capacitor and the loop is as low resistance as possible. Any ohmic resistance in that connection kills your efficiency and bandwidth. So, ideally you want to connect the loop directly to the capacitor, solder, weld it, bolt it, but don't put spindly little wires on it because that'll kill it. Obviously it's a lot easier to do that than, it's easier to do that than maybe a complicated ground plane structure. So a short whip or dipole is generally capacitive or has negative reactance, so it needs inductance to be added to bring the antenna into resonance. But the converse is true of a small loop. You need a capacitor to bring it into resonance, not an inductor to bring it into resonance. And it just so happens to be true, I nicked this quote from somewhere, I can't remember where, it just happens to be true that high quality low loss capacitors are much easier to build and make than high quality low loss inductors. So as a consequence of that, therefore, a small loop resonated by a capacitor will have a much higher Q and efficiency than a short dipole resonated by an inductor, if that makes sense. So you can build very high efficiency, 90% plus efficient loops quite easily. Well, you can see how easy they are to build. I mean, these capacitors I bought as kits take about 20 minutes to build the capacitor, and then you just make a loop and connect it on. It's not hard. I mean, let's say I built the little loop on a Sunday afternoon in about, I don't know, an hour, something like that. It was pretty easy to build. And there's lots of online calculators. You don't have to do all the maths yourself. There's some really sexy online calculators. You just put your loop sizes, you know, what frequency you want, and it will tell you how big the loop needs to be, how much capacitance you need. It's pretty easy. So where's the catch? I mean, what, you know, there's, you know, don't get something for nothing. So the laws of nature and electromagnetics cannot be violated, obviously, like any law of physics. The unavoidable price you pay for operating with an electrically small, high efficiency loop antenna is very narrow bandwidth. So they're super low bandwidth, and that's why you need the tuner. Because if you, I mean, we're talking like 10, 20, 30 kilohertz wide. So I've got a picture on the next slide that shows this. So any small loop antenna will inherently be narrow band and require a tuning to the chosen operating frequency within an HF band. So a magnetic loop antenna at say 7 meg will have a bandwidth of like 10 or 20 kilohertz, which is only 0.2% of its the frequency, you know, you're on. So these are a couple of plots I took with my my VNA, which I don't know what I've done with it. It's around here somewhere. So the left-hand one is my it's not 136, is it 132? Something like that, you know what I mean. An N-fed long wire in the garden. So that's the bandwidth. So exactly the same scale, 6 meg to 8 meg. So they're sitting on at 7.1 meg, give or take. So you can see the difference, and that's the SWR plot of that big loop compared with the long wire. So you can see how narrow band it is. As you go up in frequency, the bandwidth tends to widen. As you go down in frequency, it narrows. So obviously that's why you need the tuner, because obviously if you're even 20, 30 kilohertz off, your SWR will be almost infinite. And then you bring it into resonance on the frequency you want, and then you end up with an SWR of about, well, generally speaking, you know, better than 1 to 1.5 usually. So the way it works is you're driving the small loop. So I've got that little box open. It's literally, there's your RF connector, and it's just connected to one side and the other side of that loop. So you're driving your RF into the little loop, and that induces rather high amounts of current in the large loop, you know, in the orders of tens of amps. So you end up with a lot of current in the loop and a very high voltage across the top of the capacitor. So for say 150 or 100 watt drive into the loop, you can end up with several kilovolts across that cap, and that's the downside of these airspace caps, is obviously they will break down. If they're damp and it's outdoors and you stick 200-300 watts into it, they'll arc over, because you'll end up with 7 or 8 kilovolts across the thing. So you've got to design the capacitor in such a way that you know. Well, again, the online calculator will tell you how much voltage is going to be generated across the cap, and then you can design the cap so that it will withstand that voltage. So a strong magnetic field is generated by passing substantial RF current through the loop, and that magnetic field in turn generates a corresponding electric field in space, and the two inextricably linked E and H components, and hence the term magnetic loop antenna. So coming to the tuner, so I decided, I thought I wanted a way of tuning the loop that didn't involve kind of, you know, sitting there, you know, like this one, listening to the noise and twiddling the thing. I wanted a sort of an automatic way of tuning it. So I started designing this tuning system. So the key sort of loop features is that it has a find my loop feature, what I called it. So you just hit the button, and what it does is it sweeps the frequency across the range you've told it to sweep, looking for the resonant point. So it basically looks for the minimum VSWR. And then once it's found that minimum VSWR, it locks to it and then tracks it. So you can move the loop either manually or automatically, and the tuner will track it. So it's a frequency-based location tracking system. So it doesn't care about the motor or where the motor is. Although they're stepper motors, I've seen other systems where people calibrate and then they find the frequency and then they measure the number of steps that the motor's moved, and that kind of does work. But then the wind bashes the loop, or the temperature goes up 10 degrees. And the whole loop dynamic changes. And with that narrow bandwidth, you'll put the motor back to the position you used before, and the loop will be miles away from where you need like an active frequency tracking system. You can't rely on physical position. So it doesn't use physical position at all. There's no feedback from the motor at all on where it is. It's got a manual real-time frequency positioning. So there's a little twiddler here on the board that you can manually tune the loop, or you can also do it on the software. I'll show you the software in a minute. There's a go-to frequency position, so you just basically, obviously within the bandwidth of the loop, you just enter the frequency you want, press go, and then the tuner will take you to that frequency, acquire the loop, lock onto the loop, and then switch the tuner out and switch the radio back in. You've got four preset frequencies per band. I mean, this is just a software thing. Rather than having to try and remember all the frequencies you want, you can preset them in the software and then just click the frequency you want and press go, and it will just slew to that frequency. You've got an upper and lower and upper frequency limits. So, because some capacitors have got ends, these don't have end stops. You can just, these sort of capacitors, you can just twiddle them around and round in circles with no damage is going to be caused. But if you've got one of these dirty great things, which is a vacuum capacitor with a huge voltage breakdown of like 25 kilovolts, this has got an end stop. If you've got a stepper motor with a big gearbox and you just keep winding it, you're going to break something. So, which is what's going to happen if I drop it. So I built in some frequency limits so that the tuner won't tune below that frequency or above the frequency you preset. There's an automatic VSWR calibration. So when you first turn the tuner on from scratch, there's a couple of trimmers on there. You use it to calibrate the analog input to get the maximum range you can from the digital to analog converter. And once you've done that, it then asks you to put a dummy load on, and then it sweeps the frequency and produces because the VSWR is not completely linear, so it produces a little lookup table, so you get a nice corrected VSWR curve. It displays, once you've done that, it displays the VSWR as well as the frequency that it's locked to. There's obviously all mechanical systems with motors have got backlash. What I mean by backlash is obviously you when the motor's running in one direction, when it reverses, there's always a mechanical slack, if you like, or backlash. And if you don't take that out, then every time you reverse direction, you build in an error and it just accumulates. So you can, when you've built your loop, you can do a few experiments and figure out how much backlash compensation you need to put in so that it always returns to the same point. And there's an LCD. So everything you can do on the tuner, on the software, on the PC, you can also do. You don't need a PC to run it. You can do everything on the actual tuner itself. So there's an RF inline. So the tuner and the radio are the tuner and the antenna are automatically switched in and out. You can either switch them in and out manually, or the tuner will switch itself out and switch the antenna back in automatically once it's locked onto the antenna. As I've said, there's a PC-based user application, so you can use it from the PC or from the board. And it's got. I've also built a bootloader. A bootloader is a software that runs on the processor on the board that allows you to reflash the firmware over the USB. So you don't need a specialist programmer. So if somebody was to build one, lots of guys have built it. A lot of, strangely, for some strange reason, a lot of them seem to be in Australia. I don't know why that is. So it's slightly inconvenient to get them a new pick. So with the bootloader, I can make software modifications, just send them a new firmware image, and then they can reflash it over the USB. So that was the prototype. So that's got a little control. I like these little off-the-shelf boards because they're like peanuts to buy. You know, like 10 quid or something. And they've got all the connectors on and everything. You don't have to build it. You just buy one of those off the shelf. There's the processor there, and there's a stepper motor driver, a little I/O expander. There's the little manual control, and there's that's the guts of that's a frequency generation board or a direct digital synthesis board. These boards are again out of China. They're like 3 quid, a fiver, unbelievable. Mine, half of them don't work, but they're cheap. So you just buy 4 and hope one works. So that'll generate three completely independent frequency outputs, which is important. I'll explain that and why it's important. And then there's a relay down here for switching the antenna and the tuner, the antenna and the radio in and out. And then that's the sort of prototype detector board, which I'll cover in a bit more detail after the demo. And then obviously an LCD display. So I built that, and it seemed to work quite well, and I was quite pleased with it. So then I went ahead and I designed a PCB. Now, it's a little bit, you can see it's a little bit on the large side. It didn't have to be that big. I mean, I could have done it all surface mount and made it tiny. But the whole point of this project was it was a self-build for anybody that wanted to build it. And I've learned, how am I going to delicately put this? I've learned in the past, having launched projects on the world, that the ham community are of an older generation, let us say, and often they complain, I can't see very well and my fingers don't work very well, I can't build surface mount, I can't see the parts. So I designed the board so that it was easy for pretty much anybody to build it. With leaded components nicely spaced out and lots of annotation. So yeah, that's why it's a little bit on the sort of large side. Larger than it needed to be. Right, so I'm gonna. Is any questions on any of that stuff? Yeah, go for it.
Just on the design piece, I looked at Magloops, and there was one thing that they said is that the maximum power was about 20 watts, because the crossover on the capacitor.
Yeah, well, I know I run them a lot higher than that. 100 watts easily into those.
And the other thing is, the diameter of the 2 loops, are those critical for the frequency? So those
Yeah.
So they both have to be calculated.
Yeah. If you type magnetic loop calculator into Google, about the first or second hit is a GitHub link. If you click on that, there's a really, which is like what the one I use, is a really lovely graphical tool. It's free. It's just a web-based tool. And it's got, first of all, you go, oh my God, this looks scary. There's millions of lines and things going all over it, most of which you can just turn off. And then at the bottom, it's really simple. You just say, right, I want a loop that's 6 feet across, or, you know, and then you just literally move your mouse backwards and forwards, and it tells you the frequency. It'll tell you what capacitance you need. And then you just play with the parameters. That's how I've designed the little loop. I wanted it for 10 meters, so 29.8 meg-ish. And I just played with it, and in the end, the optimum size was a loop that was 75 centimeters across, and a capacitor with a range of about 11 picofarads up to about 70 picofarads. And that would take me all the way down to 20 meters, and all the way, but not very efficient, and all the way up to 10 meters where it's like 90% plus efficient.
Where did you get the capacitor from?
There's a guy, I should have put a link on the thing. I can send a link. There's a guy in Turkey. He's a really nice chap. I've spoken to him a few times, and he sells them as kits. You just tell him how. Well, he's got various preset ones, but he'll send you as many plates and stators and bits as you want. He sends you the 3D printed. That whole cap arrived in the post within a week from Turkey, courier, and I think it was about 60 quid plus the postage. Which, when you compare how much people on eBay are charging for bits of rubbish they found in old radios, which are completely unsuitable because the plates are too close together and they will break down at 10 watts. That cap there on the little loop is configured as a butterfly, so you're actually connected to the two. You're connected to the two stators, to this stator and that stator. This butterfly is not connected to anything; it's just spinning in the middle. So that's got a breakdown voltage of about 7 kilovolts, if you configure it as a butterfly, you get less capacitance range, but a higher breakdown voltage. Or you can connect the stators together and use the rotor as the other connection, which gives you a more capacitive range, but a lower breakdown voltage. Another advantage of using the butterfly is if you were going to connect to the rotor, I don't know if you've ever looked at capacitors that work like that. You've got like a brush mechanism, because obviously the rotor is rotating, so you've got to have some sort of like brush mechanism to connect to it. And that introduces resistive losses, which are a bad thing for magnetic loops. Whereas if you connect to the stators, you literally just bolt straight on and there's no loss. So yeah, butterfly is the way to do it. Right, I'll try and, hang on, bear with me a minute, I'm going to attempt. Right, okay, that's good. Anything naughty on here, have I now? So that's my software. So if I connect to the tuner, I hope this is going to work. So that's the software I've written for. Oh, it's even reasonably legible. So I'll just quickly go over what it does. So as it says, magnetic loop tuner. You've got some fine controls at the front, so you can course tune in either direction, and you can set how many steps you want those to be. There's a sort of emergency stop button, if you like halt just kills it, stops it, whatever it's doing. And a connect and disconnect button for the USB. So it's not a COM port. The tuner looks like an HID device to the PC, like a mouse or a keyboard. Then you've got this, well, it's easier to demonstrate this. Here's the find my loop. So it's currently hooked up to that loop there. So if I hit find my loop, hopefully this is going to work. Now I've put, it found, yeah. If you've already found it, it automatically locks to it. So if I hit it again, it will scan for it. There we go. So it's scanning between 6 meg and 14.3 meg, because those are the limits I told it to use. So it's not moving the motor, it's just sweeping the frequency across the loop. You can see the frequency sweeping here till it gets to 14.3. There, and it's acquired it. So that loop is resonant at 7.105 megahertz, which is like, that was what I was using the other day on the 40 meter band. You know, I was on 40 meters, 7.1 meg. Now, if I want to move it, I can move it manually. I'm going to try and do this without knocking the little board over. Hang on a minute. I'll just change the rate. Right, okay. So if I twiddle the little control, can you hear the motor moving? Yeah. And you see the frequency going up? So it's the tuner's tracking the loop in real time, so it's locked to the loop. It'll lock to the loop plus or minus about 100 kilohertz. So if you try and move it too much, if you jump it right out of 100 kilohertz, it will lose the loop, but within that range, it will keep it. So if I want to move it to say I want to move it to like 8.1 meg. And it'll have a look there, and it's moved it to 8.1 meg, and then it's, so we'll see if we can move all the way up to the 20 meters. So if I move it to, say 14.1 meg, and hopefully it won't run out. If it goes too far, it will give you a warning that it can't find the resonant point.
Will that software work with Windows 11?
Yeah, that is Windows 11. Say again?
Any conversation about it.
It should do.
Stuff that doesn't work.
It should. I haven't found anything it doesn't work on. I've got some right old tin boxes, as Mike Oldfield said. The steps get larger. It's not linear, obviously, because the capacitors are not the capacitor's plates are not completely round, so it should get there in a minute.
So is it actually checking its resonance all the way through?
Sorry, say again.
Is it actually checking its resonance all the way through?
Yeah, it's tracking. It's moving the motor and then sweeping across. It's having a little shimmy around. There, it's acquired it at 14.1. So yeah, it's not. It doesn't know where the motor is. It has no knowledge of the motor position. It's moving the motor, and then it's not sweeping the whole range of the antenna because it's already found it. It's just doing a little. It's doing a little scan like that, and then moving the motor and just keeping an eye on where the loop is until it gets to within about 30, 40 kilohertz of where you want it to be, and then it has then it reduces the amount that the motor moves to a very small amount and has a little shimmy around until it gets it as close as it can and it goes, right, that's as good as I can get it. So each motor movement is about 5 kilohertz of frequency movement. And now it'll just sit there. But you can see how sensitive, if I whack this loop a bit, see, look, it's all over the place. So that's what you've got to contend with. If that's outdoors and it gets blown around a little bit, and you've tuned it by motor position, the wind knocks it a bit, and you're out, you're gone. You know. So so at the moment the tuner's connected. So there's a mode which would allow you to. There's a mode where the tuner will automatically disconnect itself and reconnect the radio, or I can just go disable tuner, and you'll probably be able to hear the relay switch. So the relay clicked, and now if you had your radio connected, you'd now be connected to the antenna on the frequency you want it to be on.
Do you use a link to the radio to tell it to change frequency?
I was hoping nobody was going to ask me that. That is
the Mark II version.
That's the Mark II. So I really wanted to do that, like cat control, you mean, from the radio. So you can you just whatever. I've basically almost run out of program space on the microprocessor on the board. So if I'm going to do cat control, you'd have to have the PC connected, because the radio would have to connect to the PC, and then this software would have to take control of the cat. It would just send commands to the board.
At the moment, you're trusting yourself to get tuned to the same frequency on the radio.
Yeah, well, what I tend to do is I'll be on the radio and I'll go, oh, there's a guy I want to talk to at like 14 or 7.1 something meg or whatever. I mean, just because the loop's not tuned to it doesn't mean you can't hear anything. It's just not. It should be higher noise and not as good. So I'll go, oh, there he is at 7.15 meg, and I just type, and then I just enter that onto the radio 7.5, tune it, clicks out, and then I make my QSO and then move on. It's you know, it's a lot.
I could see myself tuning what I think is on VFOA, and it actually, as soon as you press the key, it goes to tuner B.
Yeah.
Because you set that up previously, and the VSWR was going to be way out.
Yeah. I mean, it's pretty accurate. If you put a VNA on it, it'll be bang on. You know, and then if you go find my loop again, you don't have to do the whole tuning cycle again. It remembers where it was, and it'll lock back straight on. So now it's actively tracking it again. So what else can I say about this? You've got my pointer. So you've got. I talked about the backlash. So you can set your backlash either backlash move or backlash manual, because you can change the backlash depending if you're using the manual controller or the automatic. I designed it so that you can a lot of guys wanted to use stepper motors, but some guys wanted to use DC motors with gearboxes, like that sort of thing, which is a completely, you drive a DC motor in a completely different way than the way you drive a stepper motor. So there's a stepper motor driver on the board here, which is in a socket. And if you want, you can unplug that stepper motor driver, and there's a chip socket underneath it, and you can pop a chip in there instead of the stepper motor driver, which is designed to drive DC motors. And there's a mode there. You can if you click that mode, it will change from stepper to DC motor. There's your frequency limits. It's tracking the VSWR. It's a bit high, but that's maybe because it's sort of in this building. It's not normally that high. It's normally about 1.5. And it tells you the calibration's okay. So that just tells you that I have calibrated the board. Otherwise, that comes up no in red. Now there's a configuration screen, which generally you don't have to touch. You can change, depending on what motor you might be using, you can change the number of steps per movement. And that close-in bandwidth allows you to change the bandwidth when it gets close to the target, how wide the bandwidth is before it starts reducing the step count, if that makes sense. You can change which way the encoder works, and also that's just basically a direction reverse button. And an auto disable, if you tick that, then as soon as when you've told it to tune to a frequency and it gets there and it says I found it, it will automatically disable itself and switch the radio back in, so you haven't got to do it manually. And then the only other screen really is presets. So I just decided this might be useful for all the different bands. You can just put in a set of 4 frequencies you might be interested in, and then if you want to go to those particular frequencies, like that one up there where it says 7.1, I can go move, back to loop control, move, and then it will track back to 7.1 meg again, hopefully. I'm quite relieved it's working, to be honest. Considering the fact that it's indoors and it's also it went all the way from Bristol strapped to the roof of my car. I'm amazed it works at all.
That's the quality of the engineer.
Yeah, it must be. That's it. Yeah. I mean, luckily, you don't have to worry about it radiating at the moment. I mean, the amount of power that this little the little frequency generator outputs is, is tiny. Is microwatts. So we'll let it get to. Is there any questions about this control system? And
Can it be? Can you actually load this onto Linux? Is this actually Python?
Oh, probably. Ask James. I'm not a software engineer. I write software, but I don't know much. Yes, the answer is because you can compile. Can you compile from Visual Studio to Linux?
It depends on the version of .NET that you're using.
Yeah.
C#, so it's not Python.
But I think you can. I've never tried it, but.
So is this software on GitHub? Is it?
No, it's actually not. Because to be honest, without the tuner, it's of no use to anyone. Because the interface between... Did it find it? Oh, there is a God. The interface between the software and the board is my own proprietary interface, so it won't work with anything else other than the firmware that's running on the chip. But what I've done is I get batches of these boards made, and I've got I don't know if anybody's familiar with the Instructables website, where you can put articles and stuff you've built and designed. Guys find it, and then they so I must have sent out about, I don't know, 20, 30 plus of these boards. And all I do is I don't make any money. I just sell the board for a tenner, and I send a microprocessor out pre-flashed with the firmware for a tenner, and then they build the board, and then I supply all the software and everything else and my time for free. So yeah, so loads of guys in Tasmania have built them for some inexplicable reason.
And all the parts and cutting this for the stepper motor and you said obviously you're getting the
Cap
from Turkey.
Yeah. Don't have to, but he's good stuff.
Where did you get the stepper motor?
Well, actually, it was supposed to arrive today. That stepper motor there is £35 off eBay from a UK-based company, next day delivery.
35?
Say again?
Did you say 35?
35 quid, yeah, with a planetary gearbox, yeah. So they do a 14 to 1, a 27 to 1 and a 52 to 1. So I use the 27 to 1. So the stepper motor is a standard NEMA stepper motor that gives you 200 steps per rev, and then you've got a 27 to 1 reduction gearbox on it. So I think in the end you end up with about, from memory, about 5,200 steps per revolution if you micro step. So it's really, really fine. Okay, any more questions on the software? I was going to, if you haven't all gone to sleep, I was going to go a bit more detail about how the tuner actually works.
Dave,
Yeah.
I see you've got it set at the moment 7.105.
Yeah.
What about if you were working somewhere around 7.028 and we just wanted to be up and down a little bit, sort of off that? Would it move in between those frequencies?
The tuner should tune you to within 5 kilohertz of where you want to be.
So sort of about 7.010 up to just
Well-
above, you know.
Well, I can only do three decimal place. I mean, to be honest, the bandwidth of the antenna means that, it's 20, 30 kilohertz wide, so, you're not, it's not like a knife edge.
No. I'm just looking at like CW frequencies down there.
Oh, I see. Yeah, I reckon if you put yourself onto a CW frequency, the bandwidth of the antenna would encompass the frequency. I've never had a problem. Not that I've ever done CW because I'm too daft to be able to learn it. I wish I could do CW because it looks like a hell of a lot of fun.
It's just that the frequencies down there are quite narrow.
Quite narrow, yeah.
060, isn't it?
Yeah.
I've worked Spain on the loop.
Sorry, say again?
I've worked Spain on the loop.
Oh, you've worked Spain, right? Okay.
And I think if you were OS, the bottom line is of course you've got hardly any noise, so
Yeah.
you can pick them up really nicely.
That is an extremely good point. You might lose a little bit on receive signal strength, a little bit, compared with a massive, great big long wire or something, but you're usually a couple of S points down on noise. So you can hear guys that just disappear.
It isn't fatiguing listening to it.
No, yeah,
Compared to a normal choir
yeah,
or whatever it is.
Yeah.
It's not fatiguing.
no, I agree.
You could go for comps and that sort of stuff, you could really do it. And to be honest with you, you could do switching if you wanted to, couldn't you? But
You could just build a monoband one.
Yeah.
Yeah.
Or you could listen with this one and
That's a good point. Yeah, that is a very good point. If you
power out the other.
absolutely, yeah, you could do that. You could listen on a loop at low noise, and then you could switch antennas and stick a kilowatt into a long wire or something. That's a good point. I hadn't ever considered that when I built the loop, but there's no reason why you couldn't switch. You receive on the loop and then transmit on the long wire.
It's aluminium strips.
Yeah,
Basically, aluminium strips are approximately kind of like off of gas, 500 a piece,
yeah,
all together with certain types of bolts.
yeah,
And Mr. Salter knows where it all came from.
yeah. I like that idea of switching antennas because that gives you all the advantage of the low noise loop and all the advantage of the high powered transmitting antenna. Maybe I do the Mark II, I'll build that in so that you can.
That was very easy. Once you
Yeah, that's easy. I mean, you could easily do that. I mean, it's just a relay switcher, isn't it? I mean, it's nothing more complicated than that.
Have you had any RF issues at all where the kit's sitting there idle, but there's something coming down the line and sending it up to the processor?
Sorry, what?
Have you had any issues with any RF coming back up to the controller for
I normally operate with a common mode choke. I normally put. I mean, this is just a patch lead I've stuck in here because I'm not actually transmitting any power into the loop. If I was operating it normally, I would have a common mode. I put a common mode choke in every RF feed to every antenna.
So how do you actually generate the RF to work out your kind of like calibration of your area? What's generating the RF for
Oh, well, I'll go through that on the next bit of the presentation, if that's okay. Right, okay, well, I'll disconnect that, and then I'll do the, how are we doing for time? All right. Okay, I'll just kill that. We'll hopefully get my presentation back. Oh, there we go. All right. Let's get to where we were. Oh, I just can't see. Hang on. Oh, hang on. Right. Okay, well, I'm going to go into how the tuner works. If it gets a bit heavy or you want to ask any questions, then just, I've tried not to make it, it's not complicated, but it's not complicated when you've designed it, is it? But but it might be for other people. So, so I've done the demonstration. So this is a block diagram of kind of how it works. So, which is where I'm going to address your question about where the RF's coming from. So it's based around, I'm a bit old school, unlike James, who's embraced the modern technology of the ESP32 sort of microprocessor board, which are kind of all the rage. I'm a bit old school, I guess. I've been using PIC microprocessors from Microchip for, I don't know, decades. So I've kind of got really, it's always the same, minute you use a particular platform, you get used to it, whether it's a radio or a microprocessor or whatever, you know. So I've used a PIC 18F, actually it's not a 2550, this is an old slide, I changed the processor to a different one, but, and this particular PIC has got an onboard USB core, so you can run software on it. So the PIC being this little 28-pin chip here, it's got a USB core on it, which will run USB 2. So rather than having like a COM port interface, it actually exposes itself as a USB 2 device. And then you've got a rotary encoder, which is just connected over general purpose I/O. And then to answer your question about the RF source, it's this little board here. I've got a picture of it later on. There's a little board that you could literally pick up, I said before, pick up out of China for like next to nothing.
That's the SI board.
It's this SI 5351, which is a little chip that tiny little chip that will generate 3 completely independent programmable clocks up to, I think it's 200 megahertz from memory. So more than enough for the HF band. And they're completely independent. It's a bit of a pig to program, if it's a lot of a pig to program. And it did take a while to get it to work. But once you've got the driver going, you just do a load of maths, come up with a load of values, shove them in registers on the board, and it generates that frequency. There's an LCD display, as you can see, so you can do everything on the board you can do on the software. There's buttons and indicators. I ran out of I/O or pins on the chip, so there's a little I/O expander, which are really useful. There's a little chip on there you can connect on a I2C is a Philips serial interface, goes back donkey's years, and that allows you to sort of spawn more connections, you know, more LEDs, more buttons. Then you've got a motor controller, which is off the shelf, which will either do stepper motor or DC, as I said before. There's a relay, which is the antenna switch. So you've got, and then the PC application we've just been looking at, and the bootloader that I talked about for reflashing it over the USB if you want. Now the bit I'm going to talk about, the crux of it really, is this bridge. The bridge is the bit that attaches to the antenna that allows you to measure the VSWR. So I think, any questions about that? I know it's a bit, so this was probably the trickiest part of the project, the bridge. So a bridge is what you attach to the antenna that allows you to measure the forward and reverse power to measure VSWR. So there's loads of them. There's tandem bridges, there's all sorts of different variations of bridges that have got little coupling transformers and capacitive coupling. You connect them to the loop and you get a voltage basically proportional to the forward and reflected power. Easy, happy days, I thought. Built a bridge. In fact, I bought one off of eBay for a couple of quid. Connected it to the loop, worked a treat. 2 voltages, did a bit of maths, worked out where the loop was, brilliant. Took the bridge off the loop, put the VNA on the loop, not on frequency, miles off. I thought, what? Did it? You know, I couldn't work out what was going on, and then it occurred to me that most of these bridges are reactive. They've got reactive elements. They've got capacitors, inductors, and this is a tuned tank circuit with an extremely high Q. As soon as you connect the bridge to the loop, it moves the loop. So you measure what you're measuring is the loop in conjunction with the bridge. As soon as you take the bridge off, the loop moves again. So I thought, so I went through a process of trying to calibrate that out. But it's not linear, and it depends on temperature, it depends on all sorts of things. I spent weeks trying to calibrate this blasted bridge and I kind of almost got it right, you know, but then it wasn't quite right, and it was always off.
Is that the words that you actually use?
No.
I just wouldn't.
I built about 3 bridges, different ones with, well, I thought I'll use a transformer coupling bridge, and then that didn't work. And I just couldn't get it to work. So in the end, I decided, well, the only way to do this is to have a completely resistive bridge with no reactive elements in it at all. But then you've got the problem, well, how do you actually, now you've got the target frequency coming off the bridge of 14 megahertz or 7 megahertz. You can't feed those frequencies into a microprocessor. So how do you turn the frequencies you're getting from the resistive bridge into something you can use on a processor? So this is a block diagram of how it works. So I'm going to try and compose myself and try to explain this. So you've got, what I use 2 double balance mixers. These double balance mixtures they've been around donkey's years. They were yeah. You can, amazing, and you can still buy them in dual inline packages because they're there on the board. And they were originally developed for old, the old phone, when people first got phones in their houses with the, telescopic antenna. They were used as the detectors in those phones. I mean, they were developed by Philips 30 years ago. And they're cheap, and they're, I don't know, 3-4 quid each. So there's 2 paths. There's a forward path and a reflected path. So the forward path is what I would call the reference path. It takes the target RF, by which I mean your 14 meg or your 7 meg or whatever frequency you're trying to tune to. There's a little resistive power splitter, just so that half the power goes this way and half the power goes that way. And on the forward path, it just literally, there's a little potential divider, and these double balance mixers have got a differential input. So you stick your reference frequency in here, and then on the loop side of things, here's the resistive bridge. So these are just, that's a 50 ohm resistor, 50 ohm resistor, a 200 ohm resistor between it. It's completely passive. There's no reactive elements in there at all. So this input on the double balance mixer is high impedance, so that doesn't load the bridge at all. So when you connect this bridge to the antenna, it doesn't change its resonant frequency. It's completely, doesn't change it. And that's the other input to the second double balance mixer. So I'll explain how that double balance mixer is working in a minute and what all this business is about. But essentially what you end up with out of here is 2 signals. One is a reference signal for the forward path, and the second is a signal which is proportional to the reflected power. So this is basically fixed, and this is proportional to the reflected power. And then I rectify it with a perfect rectifier, which I'll explain a bit more in a minute, which is basically a diode with an op-amp wrapped around it. And then that produces a half-wave rectified signal proportional to the reflected power. Then there's an envelope tracker, which basically just turns it into a DC level. And then there's a gain stage. So now what you end up with after all this is an analog signal which is proportional to your forward power, and an analog signal proportional to your reflected power. And once you've got those two signals, you feed them into the microprocessor, do a bit of maths, and you can work out your VSWR. And I say the important bit, this bridge does not move the antenna, which was the bane of my life. So this is a snapshot of the schematic for the bridge, and you can see here's the bridge here. So you've got 100 ohm, 200 ohm resistors. Just it's important the bridge is well balanced. So I used high tolerance resistors, and then I put them in parallel to improve the tolerance even more. So that's 50 ohms basically, 50 ohms, and then a 200 ohm resistance between them. Essentially, this is just the relay, the switching, the tuner, and the radio. So here's the radio, here's the antenna. So the antenna hangs off after this leg of the bridge. There's the differential output from the bridge that goes off to one of the double balance mixers. And there's the forward, there's the little potential divider that we had in the other picture. That little potential divider there is there, and that gives you the signal to the other double balance mixer. And this is just the relay controller down here.
Could you just go back to that previous one?
Yeah.
Tell me why you've got a target RF minus 100 kilohertz.
I'm getting to that. I was hoping somebody was going to ask that, because that's the critical bit. So the double balance mixer. So it operates 500 megahertz. I was selling it short when I said 200. I think there's two versions. I think one's made by Philips and one's made by National Semiconductors. And I think the National Semiconductors is the SA612, which is got a higher. I think it's got a higher frequency range. So it's super low power. Not that that's relevant. You can have an internal or external oscillator. So. And it's got a differential input. Now, I don't know how many people know what a double balance mixer does, but it essentially has got you've got two inputs. You've got two frequency inputs. So in this case, F bridge is the frequency that you're trying to tune to, 14 meg or 7 meg or whatever, and then you have a local oscillator. And then what you get out of the bridge is you get your target frequency plus a local oscillator, and the target frequency minus a local oscillator. So you end up with a spike in the middle, and so you had 14 meg there, you end up with 14 meg minus local oscillator, 14 meg plus local oscillator, either side. That's not a double balance, that's what a mixer does. So the key bit is, what happens if you make the local oscillator the same frequency minus 100 kilohertz? So that's where this little frequency generator comes into its own, because you've got two frequency outputs. You make one of them 14 meg, say, and you make the other one 14 meg minus 100 kilohertz. And they're always, the second frequency is always 100 kilohertz lower than the target frequency as it tracks. If you plug that into that little equation, you get F bridge plus F, so you get 14 meg plus 14 meg. I'm just using 14 meg as an example, whatever you're trying to tune your antenna to. So you get 14 meg plus 14 meg minus 100 kilohertz. You're not interested in that term because that gives you 28 megahertz minus 100 kilohertz. Forget that term. This is the important one. The F bridge, the 14 meg cancels out. You get 14 meg minus 14 meg plus 100 kilohertz. So what you end up with is a term at 100 kilohertz, which is proportional to the reflected power. And 100 kilohertz is something you can feed into a microprocessor, or it's something you can do something with. So that's the key term. This term here is a high frequency term. You can just filter that out. Does that make sense? So yeah, that's the key. Is the key with that frequency generator is it's got two frequency outputs, and you can offset them by whatever you want. You could. I think the minimum you can offset is something like 5 hertz. I think it will do something ridiculously small. I chose 100 kilohertz. I played with different frequencies. I settled on 100 kilohertz because it just seemed to work the best. So I didn't just sort of guess how this was going to work. I did a SPICE model. I don't know if anybody's familiar with SPICE. It's a analog modeling software. This is the free version called LT SPICE. You can just download it off of their website. I think there's a limit of like 500 components or something. So I modeled it. So here I created there's a capacitor and an inductor, so that looks a bit like a Magloop, an inductive capacitive loop with a 50 ohm load. There's the bridge, two 50 ohm resistors with a resistor in the middle and another 50 ohm. So that's the bridge modelled. LT SPICE actually has believe it or not, actually has the SA612. It has the model. Didn't have to design the model. It has the model in its library. So there's the double balance mixer. There's the inputs to it. There's the local oscillator. There's the power supply for the double balance mixer. And then you get an output from the double balance mixer, which you then put through the rest of the processing. There's a filter. Then there's a perfect rectifier, which I'll cover in a minute. And then there's a envelope tracker and a gain stage. And then that output goes directly to the microprocessor.
Not making light of it, but how many hours did you actually put?
Sorry, say again.
Not making light of it, but how many man hours did you put into just that section?
You lose track, don't you, over time? You lose track. I don't know.
It must have been a lot.
Well, yeah, I guess. Yeah, I don't know. I don't really think about it like. I don't know. Quite a lot, yeah. I think probably the lion's share of the time is probably software development.
But it's fun.
It is fun. So you don't think of time, do you? You just got to be careful. You occasionally go in and speak to the wife. That's not a problem anymore. And I shouldn't have said that. I'm being recorded on it. Go on. No, it's not a problem anymore. And the only thing I've got to be careful of is, like, you know, my daughter comes down to the workshop and helps me with a lot of she used to help me a lot more than she does now, because she's older now. But when she was little, she used to come down. We did all this stuff for hours, you know, messing about. So yeah, I don't know. I probably a month or I don't know, 6 weeks of sort of evenings and messing around. This is a little picture. So I was talking about that output from the double balance mixer and the fact that you get those two terms, this term and this term. One's double the frequency and one's the frequency you want. So this is a plot of the output of the double balance mixer. This is a plot. Oh, blast! It went the wrong way. This is a plot of kind of the output of the double balance mixer. And what I'm showing in these two plots is the effect of this little filter. This little filter is got a cutoff of about 150 kilohertz. So it gets rid of that high frequency term from the double balance mixer that we didn't want, the 14 plus 14 minus 100 kilohertz term. If you look at this, so this is without the filter. So there's the 100 kilohertz signal that we want, the second term from the double balance mixer. And over here is the one that we don't want, and all this is just harmonics and mixing products and rubbish. So, and as soon as you put the 150 kilohertz low pass filter in, there's the term we want. And then all the other, I mean, these are like, what's that? 60 dB down, these terms over here. So it's suppressed, what was up here is now all the way down here, sort of, 45 dB down? Because although it's only a single pole filter, you got its cutoff is 150 kilohertz. This is 28 megahertz. So by the time you get there, it's absolutely killed it. So you only need a little RC filter because of the massive difference in these frequencies. So to all intents and purposes, this is not visible. But at this point, it's still, an analog sinusoidal signal. It's it's a 100 kilohertz signal proportional to the reflected power, but it's still an analog signal or a sinusoidal signal. Oh, and there's a couple of plots from my spectrum analyzer. So there's the 100 kilohertz. There you go. So marker 100 kilohertz. That's the oh, there we go. That's the forward path, and that's the reflected path. So those are your two wanted signals after you've done the filtering. Now the next thing you want to do is convert it from a sinusoid into basically half-wave rectifier. So you turn it from this into that. You can't just stick a diode in there, because a diode has obviously got a diode generally as a diode drop, or a forward bias voltage of 50 to 700 millivolts, depending on which diode you use. And the output of the double balanced mixer is pretty small. I could have put a gain stage in, but in the end, what I did was if you take a diode and you wrap a op amp round it, it's still the diode, but you get rid of this diode drop. So they're usually termed like a perfect rectifier. So the op amp is a precision rectifier, so it's basically a voltage follower. So when the input voltage goes positive, the feedback ensures the output voltage of the op amp rises to match the input voltage, thus eliminating the diode drop. So you get a diode, but without the drop. It's basically, so you can put a teeny weeny little signal in, and you don't, if you just put that onto a diode, you wouldn't see it, you just get lost. And then, so now you've got a signal which looks like that, half-wave rectified, but you want to turn it into a DC level so that you can feed it into the processor and put it through an analog to digital converter and measure, turn it into a number. So you need a DC level. So it's a simple envelope tracker. So it's just a capacitor with a resistive bleed resistor. So once you put the half-wave rectified signal into that, what you get out, if you pick your RC network correctly, is you get approximately a DC value, but still not very big. So the final stage is to add some gain to get it up to, 4 or 5 volts, something like that. And that's what the little, there's a couple of little trimmers on here. Those trimmers adjust the gain of the output stage. So as part of the calibration, it sends a fixed frequency on both forward and reflected paths, and then you tweak the trimmers to get, well, the ADC on the processor has got a range of 0 to 1023 or 10-bit range. So you tweak the trimmers to almost fill that range, take it up to about 900, 950, and now you've almost filled the range of the analog digital converter. So that's set the gain. You do that for both forward and reflected paths, and that's pretty much the calibration done. Does that make sense? Yeah. Oh, and that's once you've got your voltages, so you've now got a forward voltage and a reflected voltage, nice and DC and reasonably stable. Then in the once you feed those into the analog to digital converters of the processor, and then you perform that calculation, forward plus reflected divided by forward minus reflected, and that gives you VSWR. And then essentially then what the tuner does is it sweeps its frequencies, the wanted signal plus the local oscillator, which is the wanted frequency minus 100 kilohertz. It sweeps across the range you've told it to, measure it, looking for the minimum VSWR, which is the resonant point of the antenna. Oh, I don't know why I put this. I said I wasn't going to do the software. This is a block diagram of the software, basically. So there's essentially a dirty great big, there's a state machine which controls all the different menu options. This is the software which is running on the processor, not the software that's running on the PC. This is the firmware which runs on that chip. There's a state machine which does all the menu options and all that business. And then there's another routine which decodes messages and basically decodes messages from the PC application, But from a hardware point, there's a USB 2 interface and an interrupt service routine for transmit and receive messaging. So you've got receive messages in this direction, transmit messages in that direction. And then everything's really based around hardware timers. So these processors have got, you don't have to use a sort of you don't have to use a software timer. You can set up, they've got hardware timers that generate very accurate hardware ticks. So I've got one running at 0.1 seconds and that's basically the tick from the whole system. That's driving the flashing of that LED, the refresh of the screen, everything else. And then the buttons are connected to the processor. When you push a button, it generates an interrupt to the processor, and then the processor services that button, whichever button you've pressed. Probably the most processor intensive thing was the calculations to drive the frequency generator. It's a great chip, but as I said before, it's an absolute pig to program. And you've got to do some, basically floating point calculations. You can't just look up some numbers and stick them in. You've got to do these horrible calculations. And every time the processor moves, every time you hear the motor move, it's got to redo those calculations to program the chip for the next frequency increment. And that is really especially for one of these little processors, because it's not even got, bigger processors have got they'll have a floating point engine or a floating point core. That little processor doesn't. It has to use floating point library functions, which are really processor intensive. And an antenna relay switch driver, I think. So I think that's pretty much it, unless anybody wants me to get questions or go back over any more of the slides. How was that?
What's the microcontroller written in?
Say again?
What's the microcontroller written in the code?
Good point. The firmware that's running on the microprocessor is written in C, and the application running on the PC is written in C#. Yeah, because I just like it. Better than C++, which is horrific. I find C# much better for handling like text and strings, and I could have written it in Python, could have written it in lots of different things, but yeah, C#. Any more questions? I mean, I've done about an hour and a quarter.
Dave,
Yeah.
You're sort of bored in everything that you've done then, so have you got a website where you can buy these bits from, or do they contact you directly?
Well, what usually happens is guys go to the Instructable, which is just a website, which has got a detailed explanation of the whole project. And at the bottom, I just basically say, if anybody wants to build it, just email me. It's not a business. I'm not selling them. And it's kind of like, it's always the same with these things. Somebody at a radio club will get a board and build it, and they'll go, oh, that looks like fun, even though they might not necessarily particularly need one. And they'll go, what's often happens is a club will buy a board, and then everybody has a little chip in and a go, and somebody will make a case for it, somebody builds it, somebody builds a Magloop, just as a club fun project, really. And that seems to be what happens, because it's just it's kind of like a fun thing to build, and it's not particularly expensive. I mean, I guess, all the parts, I mean, there's nothing on there that costs more than about a £5. I guess it's probably 30, 40 quid's worth of bits. And I say I sell the processor and the board for cost. I mean, it's just, the boards cost me about £8. I sell them for about a tenner. The processors for about a tenner. And then whatever postage, in the UK, like a few quid, and that's it,
Are you going to give us your email so we can...
Yeah. I don't know why I didn't put it on the slide. That was a bit stupid, wasn't it?
We'll put the Instructable link on the
Yeah.
video and on the website. All the
Yeah, that's a good idea. Yeah. Or I mean, it's on QRZ, G7IYK. Yeah, my email is on there, and also, but if you go to Instructables, and just my surname, then I've got a whole bunch of projects like this one, and then I think there's 9 on there. a wisp.
Just going to put it.
Yeah. I've done a whisper beacon, and there's another project. There's a hex beam project that's which after the winter needs a bit of TLC. I must admit. But there's lots of other projects on there. So, but if you got anybody got any more questions about the actual?
Just on the physical making of the loop. And
Oh, hang on.
forming up the round,
Yeah, sorry.
yeah, the physical form. of
Yeah.
the loop. I mean, does that material just form up into that round shape easily? Or do
Oh,
you
yeah.
write around something?
Oh God, it's so easy to it's really easy to make.
Yeah.
I mean, it's not like copper pipe. The good thing about it is, unlike copper pipe, with just kinks,
Yeah.
or you need a pipe bender. Literally, to do the little loop there, I just went, right, 75 centimetres. I sort of chalked it out on the workshop floor, and I just sat there with my knee doing that for a bit with a cup of tea until I got it about right, and then sort of like, shimmied it around a little bit until it was about the right size. I mean, it's not even critical that it's completely round. You can make them hexagonal.
I've seen them just made out of a bit of coax.
Yeah.
And how do you form the smaller one? Which is
Saying that is made from that the soft copper pipe they use for heating pipe. Microboard, that's the word. You get it in B&Q for like 10. Well, I don't know how much it is. I bought about 4 meters of it years ago, because the little loops. The rule of thumb is whatever the size of the big loop is, you make the little loop a fifth the diameter, or a fifth the circumference. That's the rule. Some people say an eighth, some people say a quarter. I think a fifth works. But you don't have to use a loop. You can use a gamma match, where you'd have like a little bit coming out here, and you just connect it straight to the. I don't use a gamma match because these are plastic coated, and you'd have to connect the gamma match to the actual outer screen of the copper, and I didn't want to break the loop. Or you can put a toroid. You can get a type 43 toroid, ferrite ring. So what I was looking for. Thread that onto the loop, and then stick about 3 or 4 turns of wire, and then just drive your RF straight into that, and couple using a ferrite ring. That works, and you can change the number of turns on the primary to match your band.
Has
Yeah.
it done anything outside in the weather with this?
Well, that box was supposed to be waterproof until it fell over and cracked, as you can see here by the little flappy bit. But yeah, that box is waterproof. These little glands are supposed to be waterproof. That's a waterproof box. That box at the bottom serves no purpose other than to hold it all together. There's nothing in there. It's just, I didn't, because it was a fairly big loop, I decided to put a box. This is just floating about. And this one didn't need it, so I just stuck a cable tie on there to stop it. Because if this moves around, that'll change your frequency, resonant point, and also your SWR will move about. So it's best to keep this and that, the main loop and the small loop, sort of fairly static with respect to each other.
So is there any reason why that little loop there is sort of squashed as opposed to...
Somebody said that you got better results by squashing it. So I decided to squash it, and it made no difference. And I haven't unsquashed it. So because this thing is not actually, it's just got a clamp. It's not screwed to this. So I could just squish it back again and move it up. Yeah, somebody said, oh yeah, if you make them oval, it works better. I don't know.
Have you ever tried to use the double rotation?
No, that's a good point. Yeah,
Swiss guide does that.
that software that I was on about, the designing software, you can put in the number of loops you want. I mean, obviously by default it's 1. You can put in as many as you want. So if you wanted this loop to be still good for 40 meters but not 6 foot across, you could use the same amount of heliacs but have a double loop. And obviously it would be half the size.
You've seen something like on eBay where they've got
Yeah, I've seen them, yeah.
double loop, and it's got a manual or
You-
an electric stepper on there.
I don't think they work as well. from what I can, if I put the double loop into the software, the design software, it seems that the bandwidth and the Q. I only played with it a little bit, but yeah, if you want to make it, if you've got literally nothing but a little balcony, and you want to put a double turn loop on there, then you can do that. And the other advantage, if you do a double turn loop, is you could have a switch on the top to use one loop or switch the second loop in. And then that way you could switch between like a 10 meter size to that size just by disconnecting the second loop from the whole circuit.
On the earlier presentation, you said about the null.
Yeah.
Is it that pointy that you can use that for direction finding? I mean, it looks like an RF loop you have on top of an aircraft for radio direction.
Oh, you mean the actual directionality? I don't think I haven't found it is directional. I mean, if I'm picking up a strong station from, say, one of the guys over in Italy pushing like 10 kilowatts or something, whatever they do, and shouting really loud. Only his call sign, obviously, but nothing else. But if I move the loop so that Mr. Italian is over here, and then I twist the loop round so that it's pointing at him, I guess, I don't know, maybe an S point. It's difficult to tell. It's definitely more sensitive in that plane, but I wouldn't say it was sensitive enough to use it as a direction finder. It's quite a wide.
So you've no point putting a rotator on it.
It's not like a Yagi, which is really directional. Yeah, I mean, yeah, a lot of people do put rotators on. Yeah, I mean, what I was planning on doing when I go up, take the little loop up to the picnic site, on 10 meters on a Sunday afternoon at about 3 o'clock with all the Americans come on board, I'll just point it east-west. Now I've got one lobe pointing towards Europe, and I've got one lobe pointing towards the US. That's why at home I got I built this hex beam for that very reason. So I use the long wire, and then if I hear somebody in the US that is a bit down in the noise, then I just spin the hex beam back and point, because the long wire's sensitive in one direction but a bit deaf behind it. So with the hex beam I can point behind it and get directionality over to the US, and then use the long wire directionality for sensitivity into Europe.
There is one thing that you haven't mentioned, is the field strength and being close to
Oh, the loop? Oh, yeah. You don't. I said this earlier on. I think I read somewhere, if you're putting about 100 watts into it, you want to be about 4 meters away from it.
Yeah.
Something like that. But that goes with any antenna, doesn't it?
It does.
But obviously with most antennas, they're 30 feet in the air, aren't they?
And it's much more than this.
And you've got a much higher field because it's at ground level and you're stood 6 feet from it, not, if that was a traditional 40 metre or 20 metre antenna, it would be 10, 20 metres in the air, wouldn't it? So
If you think about it, if you've got something like that in the garden and you're not seeing it, and then somebody walks past it, particularly if it's a child
Yeah.
or something like that, they don't know the difference.
I mean, if when I'm up at the picnic site, I'm QRP anyway.
Yeah.
So I'm like, I use my 705, which is in the bag there, and I'll either have it on battery at 5 watts or on the car at 10 watts. So I wouldn't.
There's no issue there.
Yeah, that's what
It's
I.
pushing about the time.
It's QRP, isn't it? Yeah, QRP.
Yeah.
Yeah, I always get dyslexia rules.
You get into the 100 watts.
Oh yeah. But then you're kind of unless you put one of those vacuum caps on there, about 100 watts is about your limit. I don't know how much. I did think about trying it I got a ACOM 700S, which is sort of 700-800 watt linear PA. I was going to jack that up and see how far I could go before I arced it over. No, but oh yeah, it'll, yeah. You often see them at you go to radio rallies, and people are selling, got some variable caps like on the bench, and you pick them up and go, it looks like somebody's been like had a welding torch on it, you know, because it's got big splats and, you know, like big burns where somebody's been, you know, that's Magloop fodder. You know, somebody's over, but it'll be one of those variable capacitors out of an old radio with a plate spacing of about 3 millimeters. And you know, they've put 50, 100 watts into it, and it's just gone, that's it, and burn a hole in it. If you're going to build one, I would thoroughly recommend buying a cat from your man in Turkey. I will get his link. Well, he's on eBay. You can't miss them because it's the only kit I've seen available.
Where did you get the copper loop from, the outer?
Well, interestingly, I bought that Heliax on eBay years ago, and it was quite expensive. Heliax 7/8, because it's Americans insist on using imperial units, don't they? 7/8 or 25 mil, whatever. But I was at Chippenham Radio Rally with Darren, whenever that was, a few months ago, and I was trying to find some Heliax, and there wasn't any available. They only had the small stuff, and I wanted the big stuff. And then as I was going out to get me bacon butty, there were two very large St John's ambulance guys stood there in the doorway with 2 rolls of Heliax behind them. And I'm like,
what is Heliax used for?
It's the feeder for like cellular towers and stuff like that.
Oh, it is.
That's 650.
Say again?
That's 650.
I guess so. Yeah. Yeah.
450s. Somebody's either 650 or 850.
I don't know which one it is, but anyway, they had these 2 rolls behind them, and I just said, "This cable, what's going on here?" You know, and he said, "Well, we heard there was loads of radio people turning up, and we had some modifications made to our tower, and these are offcuts. We were going to put them in the skip, and we thought we'd just bring them along."
Put it in our skip.
Yeah, and I said, "Well, what do you want for them?" He went, "Well, I don't know. I just made a donation to the St John's ambulance, and he gave me the 2 rolls of cable for like 10 quid or something." So that's what so this is St John's ambulance Heliax. I mean they still had the dirty great big connectors on. I mean, they were a bit bashed about. The cable was a bit sort of bashed about, but
The connectors are...
yeah, I don't know what the huge great connectors. I mean, like this sort of size. Say again?
40, 50?
Are they? I don't know. I got 2 of them.
That's some 450s.
I mean, the other end of the cable looked like it had been cut with an axe. I mean, it was just like, you know, or a hacksaw or something. I mean, it's very easy to cut the stuff because it's you've got a central core. I should have brought a little. You can see it if you look at that one. There's a central solid core which is almost exactly the same as that copper heating pipe, a bit smaller maybe 10 mil. And then you've got like a PTFE, I guess, dielectric insulator inside. Then you've got the outer core, which is really nice and easy to bend and really easy to solder to. Because when the RF's flowing around the loop, it flows on the skin. So there's no advantage in making it a solid copper core. It makes no difference. All the energy flows within literally fraction of a millimetre of the skin of the outer core.
Have you seen the YouTube guy that actually uses foil?
Foil, yeah, that would, that would work, yeah.
Would you retain in that box the larger one?
Yeah.
Would you retain the coax coming out of the box? Because I was thinking about actually using 450 connectors and 450 bulkheads, but that I don't know how you actually do it. I can't see it.
How did I connect to it?
How do you actually hold it in place? In other words, anchor it into
What?
the case.
Oh, just a Jubilee clip either side.
Okay.
Simple. Yeah, it's just a Jubilee clip. I actually only put those on because I thought I've got to take this to Swindon and strap it to the car.
Yeah.
And before that, I didn't need any anchoring at all because it just sits so nicely and it doesn't go anywhere. But then I thought, well, if I'm going to put it on the car and cable tie it to the roof, I don't want those sort of wanging around because I'm just going to. I mean, at the moment, it's just soldered on using 32 amp ring main cable, the solid copper. But this week I've got a couple of meters of 8mm copper braid, because it's really important that you minimise these this resistance. Any resistance you add in this loop will kills the bandwidth. Even a few tens of milliohms is enough. You can do on the calculator, that online calculator. One of the fields is ohmic resistance, and it starts off at 0, perfect. You start adding a bit of resistance in, and you can see what it does to the bandwidth on the curve.
The Somerset Police pursuing you because you was in a UFO.
So, well, I was a bit worried about that. The bit I was most concerned about was did the loop stick out further than the wing mirrors? Because technically, if it sticks out further than the wing mirrors, yeah, I was a bit worried about that. So I sat in the inside lane and just tootled along behind a truck at 60. And I figured that if anything fell off, I'd blame the truck. So,
That's the technique.
yeah. Slipstreamed a truck. But earlier on, with the weather, I don't know what it was like here, but it was like horrific in Bristol. I thought, of all the days, I've got to get the loop to Swindon. The other bit on the construction, these sort of two capacitors are constructed slightly differently. So this one is not a butterfly cap. So on this one, the stators are wired together because I needed more capacitive range. So I've wired the stators together, and I'm using the rotor as the other connection. That gives you more capacitive range, but less breakdown voltage. But the only problem with that is you've got to make sure you don't connect anything metal to the rotor, like this motor. So there's two flexible couplers, and then in between is like a little PTFE insulating rod, so which doesn't twist. So there's no backlash in that insulator, or none that I could measure. But it means that this motor is not physically connected to that rotator. But this one's different in that one connection goes to one stator, and the other connection goes to the other stator, and this rotator is not connected to anything. It just spins in the middle. You get less capacitance, but you get double the breakdown voltage. So that one breaks down at about 7 kV, and that one would break down at about sort of 3-ish, something like that. So potentially the little loop would handle a lot more power. I don't know how much power it'll take, but yeah.
Good. Thank you very much.
Yeah, thank you.
Yeah,
Thanks.
Quick round of applause for Dave.
Well, if anybody wants to build one, I've got boards and processors. So, and schematics and a list of parts and all the rest of it. It's, yeah, it's a fun project.
Thanks, really